Hello and welcome again. I am your host Harshit Sinha, continuing the second part of the topic Buildings Energy Efficiency Program in India. Taking lead from my previous presentation. The Buildings Energy Efficiency Program (BEEP) in India is a key initiative aimed at reducing energy consumption in the building sector, which accounts for a significant share of national energy use. The program promotes the adoption of the Energy Conservation Building Code (ECBC), energy efficient design practices, and advanced technologies in both commercial and residential buildings. By integrating passive design strategies, efficient appliances, and renewable energy solutions, BEEP helps lower energy demand, reduce carbon emissions, and improve thermal comfort. It also focuses on capacity building, awareness, and market transformation to create a sustainable, energy-efficient built environment for the future. Now let us explore the remaining part of the topic. Slide 2. ENS Features and Coverage. The Energy Efficiency in Residential Buildings (ENS) code has been developed to improve energy performance in India's housing sector, addressing diverse climatic conditions and housing typologies. Its features and coverage ensure a structured approach to enhancing building efficiency while maintaining design flexibility. A key component is building envelope performance, which specifies requirements for thermal insulation of building envelopes. This includes maximum allowable thermal transmittance values, U values, for roofs and walls. These values are climate-specific, ensuring that construction aligns with India's 5 climatic zones to maintain comfort and reduce energy demand. The code also introduces fenestration requirements, setting maximum window-to-wall ratio, WWR, limits and minimum visible light transmittance, VLT, standards. These provisions aim to balance daylight access with reduced heat gain, thereby minimizing energy consumption from artificial lighting while preventing excessive solar heat ingress. Another significant feature is the residential typology focus. ENS covers multi-story apartment buildings, row houses, and individual dwellings, ensuring adaptability across diverse forms of development. This inclusivity ensures energy efficiency benefits extend from urban high-rises to smaller housing units. Additionally, ENS emphasizes integration with housing programs such as the Pradhan Mantri Awas Yojana (PMAY). By embedding efficiency measures into large-scale housing initiatives, the code ensures affordability and accessibility of energy-efficient homes for lower-income households. Overall, ENS adopts a performance-based approach, offering flexibility in design while ensuring compliance with energy standards. By combining building science with practical housing needs, ENS strengthens India's transition to a sustainable, energy-efficient residential sector. Slide 3. ENS Implementation and Incentives. The Energy Efficiency Norms and Standards (ENS) Implementation and Incentives Framework focuses on driving sustainable development in the building sector through both technical assistance and financial mechanisms. To facilitate adoption, the Bureau of Energy Efficiency (BE) has designed a comprehensive support system that emphasizes capacity building for architects, builders, and municipal officials. This includes the formulation of building design guidelines, specialized training programs, and the provision of technical tools for real-world application. In addition, partnerships with academic institutions ensure that best practices and innovative approaches are widely disseminated, fostering a skilled workforce equipped to integrate energy efficiency into urban infrastructure. On the financial side, ENS implementation is reinforced through incentives and market-driven mechanisms that reduce adoption barriers. These include property tax rebates for ENS-compliant structures, preferential lending by banks for energy-efficient housing projects, and priority project approvals for developers adhering to energy norms. Such measures provide direct cost advantages and make energy-efficient construction more financially viable. Pilot initiatives in cities such as Delhi, Mumbai, Ahmedabad, and Bengaluru demonstrate the practicality of these approaches, offering scalable models for replication nationwide. Slide 4. Eco-Niwas Samhita (ENS) Introduction. The Eco-Niwas Samhita (ENS) marks India's first comprehensive code for energy efficiency in residential buildings. Introduced by the Bureau of Energy Efficiency (BE) under the Ministry of Power, ENS serves as the residential counterpart to the Energy Conservation Building Code (ECBC), with a tailored focus on diverse housing typologies and usage patterns across the country. Its foundation was strengthened through the Energy Conservation Amendment Bill 2022, which extended the scope of the Energy Conservation Act to include residential buildings, thereby institutionalizing energy efficiency within the housing sector. The ENS has been designed with a phased approach to address the unique challenges of India's residential sector. ENS Part 1, 2018, concentrates on the building envelope, covering critical elements like walls, roofs, windows, and shading devices. By emphasizing thermal performance and reducing heat ingress, it ensures better indoor comfort while lowering cooling demand. ENS Part 2, currently under development, will broaden the scope by targeting mechanical and electrical systems such as HVAC installations and lighting in residential spaces, thereby creating a holistic efficiency framework. What sets ENS apart is its balanced focus on energy efficiency and practical feasibility. While promoting sustainability, it recognizes the socio-economic constraints of the housing sector and proposes implementable strategies that reduce energy demand without compromising affordability. Slide 5. ENS Estimated Impacts. The Eco-Niwas Samhita (ENS) is projected to deliver transformative impacts on energy consumption, household savings, and environmental sustainability in India's residential sector. By focusing on improved building envelopes and passive design strategies, ENS-compliant homes can reduce cooling energy demand by 20 to 30%, a significant achievement in a country where cooling requirements are rapidly increasing due to rising temperatures and urbanization. From an economic perspective, ENS also ensures notable life cycle savings, with an estimated reduction of nearly 40,000 rupees per household in a typical two-bedroom apartment over a decade of occupancy. These savings become even more substantial in warmer climate zones, thereby directly benefiting households while alleviating energy burdens. One of the most significant impacts of ENS lies in indoor comfort. By improving thermal insulation and ventilation, ENS homes can lower indoor air temperatures by 4 to 5 degrees Celsius during hot summer months. This reduction enhances the quality of life, particularly in regions without widespread air conditioning, while also minimizing dependence on mechanical cooling solutions. At a national scale, widespread ENS adoption could reduce the peak power demand by nearly 15 gigawatts by 2030, equivalent to avoiding the addition of 1,000 megawatts power plants. This directly contributes to energy security and reduces stress on India's electricity grid. Beyond energy savings, ENS generates co-benefits such as improved thermal comfort, reduced carbon footprint, and enhanced resilience against climate change. For low-income households, especially, the improved building performance translates into healthier living conditions while simultaneously lowering economic vulnerability. Thus, ENS establishes itself as both an energy efficiency strategy and a social equity measure for India's sustainable future. Slide 6. Energy-efficient material and practices in residential. Promoting energy efficiency in residential construction requires a holistic approach that integrates innovative materials, passive design strategies, and context-specific practices. Modern envelope technologies play a central role, with solutions such as insulated walls, autoclaved aerated concrete, AAC blocks, insulated concrete forms, and cool roofing systems reducing heat ingress while enhancing structural performance. High-performance glazing, low-emissivity coatings, and UPVC-framed windows further minimize energy loss and improve indoor thermal comfort. Complementing advanced materials, passive design strategies emphasize natural ventilation, daylighting, and climate-responsive architecture. By incorporating courtyard planning, proper orientation, and shading devices, homes can optimize natural cooling and lighting, thus reducing dependence on mechanical systems. Landscaping with vegetation also contributes to microclimate regulation while supporting energy savings. Equally important are locally adapted solutions that align with India's diverse climatic conditions. Region-specific approaches such as mud blocks, cavity walls, and locally sourced sustainable materials reduce both costs and carbon footprints while addressing cultural and environmental contexts. The water-energy nexus is another key dimension, as efficient water management directly reduces energy consumption. Rainwater harvesting, low-flow fixtures, and grey-water recycling systems minimize water stress and reduce the energy required for pumping and treatment. Additionally, energy-efficient household appliances ensure further reductions in consumption. Slide 7. Pradhan Mantri Awas Yojana (PMAY) and Sustainability. The Pradhan Mantri Awas Yojana (PMAY), India's flagship program to achieve housing for all, has progressively integrated sustainability and energy efficiency into its framework. By embedding green building practices within its Affordable Housing in Partnership (AHP) component, PMAY not only addresses the housing shortage but also aligns with climate-responsive and resource-efficient development. The scheme emphasizes the adoption of sustainable materials and energy-efficient designs, guided by principles such as climate-sensitive site planning, use of eco-friendly bricks, installation of solar water heating systems, and incorporation of rainwater harvesting. Energy-efficient lighting and appliances are also encouraged, reducing both household energy demand and environmental impact. Several state-level initiatives have enhanced PMAY's sustainability focus. For instance, provisions like the Flow Space Index (FSI) relaxation incentivize developers to adopt energy-efficient measures. Furthermore, the Bureau of Energy Efficiency (BEPA), under the Ministry of Housing and Urban Affairs, has collaborated with states to integrate energy efficiency financing platforms (EEFPs) into affordable housing projects. Demonstration projects in Gujarat, Maharashtra, and Tamil Nadu illustrate how incorporating sustainability can deliver dual benefits, lowering long-term energy costs for households and reducing pressure on natural resources. These projects highlight that affordable housing and sustainability are not contradictory but complementary goals. By mainstreaming eco-friendly designs, water conservation measures, and renewable energy technologies, PMAY demonstrates that affordable housing can achieve resilience, comfort, and affordability while contributing significantly to India's sustainable urban development agenda. Slide 8. Star Rating for Buildings. The Star Rating Program for Buildings, developed by the Bureau of Energy Efficiency (BEPA), provides a standardized benchmark for evaluating and comparing the energy performance of buildings. Unlike prescriptive codes that focus only on design specifications, this voluntary rating system emphasizes actual energy consumption measured in kilowatt-hours per square meter annually. The program covers various building typologies such as office buildings, shopping malls, IT parks, hospitals, and BPOs, distinguishing between daytime use and 24-hour use facilities. By categorizing buildings based on operational patterns, it ensures fair and relevant comparisons. The rating process involves the assessment of real-time energy usage, considering climate zones to ensure accuracy. Buildings are rated from 1 star to 5 star, with higher ratings reflecting superior energy efficiency. This initiative promotes reduced energy consumption, operational cost savings, and sustainability while encouraging developers and owners to adopt energy-efficient technologies and practices. Valid for 3 years, the ratings require periodic reassessment to ensure continued compliance and performance improvements. By integrating visibility with performance, the star rating system strengthens accountability, motivates energy-conscious design, and contributes significantly to reducing the environmental footprint of India's rapidly growing building sector. Slide 9. Star Rating System Impact. The Star Rating Program, initiated by the Bureau of Energy Efficiency (BEPA), has significantly influenced India's commercial building sector by establishing clear energy performance benchmarks and encouraging market transformation. Since its inception, over 1,500 buildings have been rated, providing a robust database of real-time performance that supports informed policy and design decisions. Buildings certified under this system have demonstrated energy savings of 100 to 120 kilowatt-hours per square meter per year, with reductions of 20 to 40% compared to conventional structures. These savings translate into substantial cost benefits for building owners and operators while enhancing operational efficiency and sustainability. Beyond direct energy savings, the Star Rating Program has also contributed to broader market transformation by promoting energy-conscious design and construction practices. encouraging building owners to adopt efficient cooling and lighting technologies, creating awareness and establishing benchmarks for other building rating systems, supporting India's transition towards low-carbon growth in line with national climate commitments. Additionally, the system has improved investor confidence, as energy-rated buildings are increasingly seen as financially viable and premium assets in the real estate market. By combining measurable efficiency outcomes with market recognition, the star rating system has emerged as a catalyst for sustainable urban development in India. Slide 10. Building Energy Performance Assessment, BEPA. The Building Energy Performance Assessment, BEPA, is a structured toolkit developed by the Bureau of Energy Efficiency, BE, to systematically evaluate, monitor, and benchmark the energy performance of existing buildings. Its primary objective is to provide actionable insights that enable efficiency improvements and promote sustainable operations. BEPA follows a multi-step methodology. It begins with energy audit and data collection, which includes a detailed assessment of energy consumption patterns, building systems, and operational characteristics through site surveys, monitoring, and utility bill analysis. This is followed by performance analysis, which evaluates key performance indicators such as the Energy Performance Index, AP, system efficiencies, and load profiles to identify areas of concern. Next, benchmarking compares building performance with established standards, peer buildings, or best practices to contextualize performance and highlight potential savings. Energy simulation tools are then deployed to test various improvement scenarios, estimate potential savings, and support decision-making. Finally, recommendation development identifies financially feasible, technologically sound measures for energy performance improvement, supported by detailed cost-benefit analysis and implementation strategies. BEPA serves as a critical decision-making tool for policymakers, building owners, and managers by identifying energy-saving opportunities and integrating them into retrofit strategies. It has been particularly impactful in enhancing awareness of efficiency retrofits, reducing operational costs, and supporting India's sustainable development goals. By addressing diverse building types, BEPA not only guides efficiency interventions but also provides a framework for linking incentives and financing mechanisms to encourage large-scale adoption. Slide 11. Green Building Revolution in India. Overview. India has emerged as the world's third-largest green building market as of 2023, showcasing a significant transition towards sustainable construction practices. The green building revolution reflects the country's growing commitment to integrating sustainability with urban development. This shift is driven by innovative, industry-specific certification systems that set measurable performance standards for environmentally responsible construction. The movement has been guided by several key rating systems such as DRHs, Green Rating for Integrated Habitat Assessment, developed by TERI and endorsed by the Ministry of New and Renewable Energy, which addresses climate-responsive design. IGBC, Indian Green Building Council, initiated by the Confederation of Indian Industry, KI, offering multiple certification programs across diverse building categories, and LEED India, adapted from the globally recognized US LEED system and promoted locally by IGBC. These frameworks have fostered remarkable growth, with over 10,000 green building projects registered as certified nationwide, covering approximately 10 billion square feet of built-up area. The sector has witnessed an annual growth rate of around 20%, underlining India's potential to lead global sustainable construction. Green building practices in India extend across diverse sectors, including affordable housing, educational institutions, healthcare facilities, IT parks, transportation hubs, hotels, and hospitality spaces. By incorporating energy efficiency, water conservation, waste reduction, and sustainable materials, these buildings minimize environmental impacts while reducing operational costs. The green building revolution thus represents not only an environmental necessity but also a strategic economic opportunity, positioning India at the forefront of sustainable urban growth. Slide 12. Notable green building examples. Green buildings showcase the integration of sustainable practices in architecture and design, aiming to reduce environmental impact while enhancing efficiency and comfort. Three notable examples in India illustrate the diversity and success of such initiatives. The Ki Sohrabji Godrej Green Business Centre in Hyderabad is India's first LEED Platinum certified building. It sets a benchmark in sustainable architecture by achieving net zero energy through the use of solar panels, efficient HVAC systems, and advanced lighting controls. The facility also integrates water recycling and conservation measures, reducing water demand by 35%. The Infosys campus in Pune stands out for its exemplary energy efficiency. Consuming 80% less energy than traditional commercial buildings, it incorporates radiant cooling, advanced building management systems, and real-time monitoring. The campus has successfully reduced its energy intensity from 200 kWh per square meter per year to just 75 kWh per square meter per year through design and operational enhancements. ITC Maurya in New Delhi, a luxury hotel, illustrates how sustainable practices can be integrated into heritage buildings. The property uses renewable energy sources and has adopted a water recycling system to minimize water usage. Its waste management, HVAC, and lighting systems are designed to minimize its carbon footprint. It is the first hotel in the world to receive LEED Platinum certification under the existing building category. These examples demonstrate the feasibility of incorporating high-performance green technologies in varied building types and climates. They highlight how innovation and sustainable practices can be adapted and scaled for broader adoption in mainstream construction. Slide 13. Energy Efficiency Innovations for Green Buildings. Energy efficiency is a core principle of green building design, and several innovations are playing a transformative role in reducing energy consumption while improving building performance. These innovations span smart technologies, advanced materials, HVAC solutions, and renewable energy integration. Smart building technologies are at the forefront, utilizing automation systems to optimize energy usage. These include IoT-enabled sensors for real-time consumption tracking, occupancy-based lighting and HVAC controls, and predictive maintenance for efficient operation. Such systems not only improve comfort but also create significant energy-saving opportunities. Advanced building materials contribute by enhancing thermal performance. Innovations such as dynamic glazing adjust based on solar exposure, while phase change materials boost thermal energy storage. High-performance insulation and cool roof coatings further reduce heat transfer, enhancing indoor climate control. Efficient HVAC solutions are another major contributor to energy savings. Next-generation systems include radiant cooling, variable refrigerant flow, VRF, systems, and desiccant-based dehumidification. These technologies are tailored for specific climatic conditions and provide greater efficiency with lower energy inputs. Integrated renewables facilitate on-site energy generation, reducing dependence on fossil fuels. This includes solar-integrated facades, hybrid photovoltaic thermal systems, and micro-wind turbines. These systems provide power while reducing emissions and operational costs. These innovations are increasingly accessible due to declining costs, supportive government policies, and advancements in material science and digital technology. Their integration into mainstream buildings is accelerating, making energy-efficient, sustainable construction a viable and attractive option across different building types and climatic zones. Slide 14. Challenges and opportunities ahead in green building development. The transition to energy-efficient and sustainable buildings in India presents significant opportunities, but it is not without its challenges. These can be categorized into three main areas: awareness and capacity, existing building stock, and data and transparency. Awareness and capacity remains a critical barrier. Many stakeholders, including building owners, developers, and local authorities, have limited understanding of the long-term benefits of energy efficiency. The shortage of professionals trained in energy-efficient design and construction, especially in smaller cities and towns, adds to the difficulty. Expanding educational programs, certification courses, and skill-building initiatives is essential to address this gap. The existing building stock poses another major challenge. With over 90% of India's 2030 buildings already constructed, retrofitting becomes key to energy savings. However, it also offers a great opportunity. Retrofitting strategies and financial models can help transform older buildings into efficient ones. Developing scalable, cost-effective retrofit solutions and incentivizing their adoption could have a profound impact. Data and transparency are also limited. Inadequate access to building performance data hampers informed decision-making, policy development, and benchmarking. Accurate data is crucial for setting realistic targets, measuring progress, and optimizing systems. Improving data collection methods and making this information accessible to stakeholders can drive efficiency and innovation. Overcoming these challenges requires a coordinated effort across policy, finance, technology, and education. By integrating strategies across these areas, India can accelerate its shift toward a greener, energy-efficient built environment, unlocking long-term environmental and economic benefits. Slide 15, Government Roadmap and Next Steps. The Government of India has outlined a comprehensive and ambitious roadmap to enhance energy efficiency in the building sector. This forward-looking strategy is designed to support sustainable development and mitigate climate change impacts. The roadmap encompasses 5 key pillars: code evolution and expansion, implementation strengthening, market transformation, technology and innovation, and capacity and awareness. Code evolution and expansion aims to ensure the widespread adoption of the Energy Conservation Building Code, ECBC, and Eco-Niwas Samhita, ENS, across all urban local bodies by 2027. It also includes introducing the ECBC 2.0 inches standards that emphasize net zero energy buildings, along with extending the codes to various building typologies such as educational institutions and retail spaces. Implementation strengthening focuses on improving compliance through digital platforms, risk assessment frameworks, and training initiatives. There is also a push for enhanced incentives and penalties to ensure better adherence to energy efficiency norms. In terms of market transformation, the roadmap plans to expand the star rating system to cover a broader range of buildings, including residential spaces. A national building energy performance database is to be developed to inform policy and investment decisions. Technology and innovation will support indigenous energy-efficient technologies, pilot projects for innovative systems, and integration of smart grid capabilities with building energy management. Lastly, capacity and awareness initiatives aim to certify building energy professionals, strengthen academic curricula related to energy efficiency, and promote public awareness campaigns targeting both developers and occupants. Slide 16. Conclusion. The Path Forward. A Vision for Sustainable Building in India. India's building sector stands at a pivotal moment as the nation transitions towards a more sustainable and energy-efficient future. Rapid urbanization has heightened the urgency for decisions that ensure buildings are designed, constructed, and operated in ways that reduce energy consumption and environmental impact. To address this, the government has adopted a comprehensive building energy efficiency framework. This includes robust codes, incentives, and capacity building initiatives. The Energy Conservation Building Code, ECBC, and Eco-Niwas Samhita, ENS, offer a solid foundation for energy efficiency across commercial and residential sectors. These efforts are being supported by financial tools and innovative policies to ease implementation. A key component of this transition is the green building revolution, driven by rising demand for high-performance buildings. These are designed to be climate resilient, energy efficient, and environmentally friendly. Additionally, the push towards net zero buildings and the integration of modern technologies such as smart energy systems and renewable energy solutions signify India's progressive stance. India is also aligning its efforts with global climate commitments and sustainable development goals. This includes mainstreaming energy efficiency into urban planning, infrastructure development, and national policies. The path forward lies in sustained commitment and collaboration among stakeholders. Through unified efforts by government bodies, private sector players, and citizens, India can establish a built environment that not only meets energy and climate goals but also ensures affordability, comfort, health, and long-term productivity. Ultimately, India's building sector is set to play a crucial role in shaping a sustainable future for generations to come. We now conclude this topic and transition to our next discussion on the Carbon Credit Trading Scheme, GE Targets 2025. Stay tuned to this channel for insightful updates, and feel free to share it with like-minded professionals in your network. Until we meet again next week, wishing you all a happy, safe, and fulfilling life.